All right, good morning. I'm Sean Knutson. I'm working with Dr. Gary Ostrander at the Manoa campus and with Dr. Bob Richmond at Kewalo Marine Lab. The main PI on this project is Craig Downs, and the co-PI is Dr. Gary Ostrander. I'm going to talk about Irgarol in Hawaiian marinas, specifically on Oahu, and any Irgarol that might be found in the coral reefs. So what is Irgarol? And why is Irgarol important? Irgarol is a pesticide, specifically a herbicide, and it is used in anti-fouling boat paints as an additive. Typically, it's put in paints such as this one on the bottom right corner with a little, it's kind of hard to see this smaller picture, but it says Irgarol stops slime. So Irgarol is added usually in about 3 to 6% of that boat paint, and it's usually used with copper oxide or cuprous oxide, and specifically it is the herbicide that's going to get rid of algae and other plant material that's going to grow on boat hulls. So that paint obviously being put to the bottom of the boat hulls, usually on small boat crafts and then on small or mid-sized yachts. And it's quite a bit more of an expensive paint. The paint with the Irgarol is quite a bit more expensive, so in talking with some of the guys at the dry docks, often it's the fancier boats, the bigger yachts, that will sometimes, in their minds, tend to be the ones that will be using Irgarol. Tributyl tin has been banned, so that has caused an increase in Irgarol use. So why should we be a bit more concerned? One of the reasons is that Irgarol is starting to be used more. And Irgarol does leach off of the boat hulls into the seawater and into the marina. So therefore, it's going to be present in the seawater. And because it's also toxic to the zooxanthellate corals, that's going to be of concern. And here's another little photo of some boats in Kaneohe Bay. So the fact that this is from West Marine, which is just down on Sand Island Access Road. I just went down and took a little photo of some of the paints that are being sold in Hawaii. And they're putting it on at the dry docks, at the Alawai dry dock and the Sand Island dry dock, and so it's out there. So I'm just going to review some of the environmental effects. I'm going to give a brief biological perspective and then a little bit of a chemical perspective. From the biological perspective, the mode of action of Irgarol as a pesticide is that it affects photosystem 2 and photosynthesis, and because of that mode of action, then it will have effects on zooxanthellate coral by having effects on photosynthesis in the corals. There's been a bit of background research that showed the effects on coral by Irgarol, such as isolated zooxanthellate at a concentration of 63 nanograms per liter, causing an inhibition of photosynthesis. Some more biological perspectives are that in intact coral, 100 nanograms per liter is causing a yield in the reduction of net photosynthesis. And then when you get to 1,000 nanograms per liter, photosynthesis is inhibited. There's been evidence as well of effects at the cellular level in cnidarian species, which is also obviously of great concern. And then coral bleaching doesn't happen to much higher concentrations of Irgarol, estimated at concentrations closer to 10,000 nanograms per liter, and I'm just keeping it all in the same units here for you so you can kind of keep track of where I'm going with this presentation. From a more specifically chemical perspective, Irgarol has been shown to stay around at a half-life in seawater for about 100 to 140 days is the estimate, and they've also now started to identify some different metabolites. And if you think of an example like Irgarol is a herbicide. Its structure is very similar to atrazine, and in the past environmental chemistry and research that's been done, atrazine is obviously hugely used, and then they started to look at also some of the metabolites of atrazine, which came to be of more concern. And so now some more monitoring is happening of this M1 and M3 and what their potential impacts may be, or their following their distribution in marinas as well. It's been shown that it's usually in the dissolved fraction of in the water instead of the sediment. Some specific experiments in the lab have been set up to show that it's not going mainly to the sediment, but mainly staying in the water phase. And they've also suggested that there's very little biodegradation from microorganisms. So this is a little table that outlines some different concentrations of Irgarol, specifically in marinas around the world. And I've highlighted the red ones here that were above 1,000 nanograms per liter. So from the numbers I gave you before, 63 nanograms per liter was the effects on photosynthesis in isolated zooxanthellae, and then 100 in adult coral was causing a reduction in photosynthesis, and then above 1,000 was blocking photosynthesis. And that's in UK, France, and Spain. That's the reports they've given, again, in nanograms per liter in the seawater fraction. In some other places, in Greece, in the United States, and Japan, are reporting like around 100 or 200 nanograms per liter. So these are some of the numbers that we wanted to kind of use as a guideline and then go and see what we could find. So the main question of this research was to see if Irgarol is present at concentrations of concern in some of the marinas and, of course, more importantly, on the coral reefs. So now is time to get to work in the lab, time to develop some methods. Starting out with the laboratory analysis, we're going to extract coral from either seawater samples, marine sediment, and also suspended materials in the seawater samples. About 10 or 20 centimeters below the surface is where the water samples were taken with brown glass amber pre-cleaned bottles and a little Teflon lid. We would take these 1 liter water samples and then take them back to the lab and extract them. The marine sediment was collected from the marinas as well with a pipe going down into the mud, lifting it up and putting it into, again, a pre-cleaned little amber glass vial with a Teflon lid and taken back to the lab. So the first part of it was the extraction of either the water or the sediment, and then in this case we used an analytical technique in the lab, gas chromatography, mass spectrometry, for the separation and then identification and quantitation of Irgarol. So this is some of the stuff that went on in the laboratory, and then once I basically worked with a bunch of water samples. I would spike them with Irgarol, some marine sediment samples, spike them with Irgarol in the laboratory, make sure everything was working, my standard curves were looking nice, and I was extracting it at a good % recovery. I tried a couple different types of cartridges to extract the Irgarol from seawater with, found the best one, and then I played with a method for the marine sediment with a assisted solvent extractor to optimize those methods. And then once I was getting some methods for each of those in the laboratory, then it was time to go out and take some samples around and do some field validations. This is just an outline of the 3 types of extractions that we did. As I mentioned, with the seawater and the water column from the marinas or from the reef, we did a solid phase extraction with a little C18 cartridge. So the 1 liter of water sample was filtered through that and then eluted, dried down to a mill, and then put on the GCMS. The suspended solids, that was taken by the seawater samples were filtered through a glass fiber filter before they were extracted. That glass fiber filter then I saved, and then I would just roll it up, put it into a glass test tube with a Teflon cap, and extract it by just sticking it in an ultrasonic bath, and then I could sonicate it for a while, flush it out a few times, rinse it, dry it down to an extract, and then run that on the GCMS, and that would be the suspended material that was coming in our water samples. And that's what's called our suspended solids, to see if any Irgarol was sticking to that suspended solids.